Good morning. This is Jerry Tuttle from Southern New Hampshire University, and I'd like to talk about the data analysis of credit scores. We all have a credit score, in fact, more than one. You probably don't remember asking permission to allow people to create one for you, but the last time you applied for a credit card or a checking account, as you quickly went through those 50 pages and ignored them, buried in there, you gave permission for people to collect information on you for a credit score. So here's Joe. Would you loan money to this guy? Why or why not? Well, of course, not just based on his appearance. We'd like more information about Joe. So what is our goal? We're going to develop a model that predicts the probability an individual will default on their loan, use these probabilities to create score intervals, assign each loan applicant to a credit score interval for a yes-no loan decision, and we want to do this in a transparent basis. We want to be able to explain numerically the reasons if we decline that person. So quickly, what is data analysis? It's the Venn diagram intersection of these three items. It's more programming than most math people want to do, more math than most computer people want to do, and it requires a domain knowledge. It requires some understanding of the data that we're looking at. What I want to do today is talk about what is a credit score, the database we'll use, some discussion of models, and then present three models. So what is a credit score? It's a number that measures how likely you are to repay your debt, loans, credit cards, bills, etc., on time. And as an example, a calculation may be a weighted average of these 5 items and then scaled into an interval such as 300 to 850. Banks don't have to lend to everybody. They discriminate. I know that sounds like a nasty word, but so do insurance companies discriminate and universities. Even a restaurant doesn't have to serve everyone as long as their rules are applied uniformly. But the data analyst needs to have some understanding of the relevant law, and some variables may not be legally or ethically used in decision-making on credit scores. The data set we're going to use is called the German Credit Data Set. It's 1994 data, that's a long time ago, in German Deutschmarks. It's 1,000 bank loan observations for 20 predictor variables, and the variable we're trying to predict is creditability, non-default versus default. The predictor variables include bank balance, loan history, loan amount, duration, assets, job categories, and surprisingly, gender, marital, and foreign worker status. Maybe that was acceptable in Germany in 1994. It certainly is not now. Here's a little description of some of the variables that are going to be used, and surprisingly, most of them are not numerical. So, for example, a checking account balance is a categorical variable, not a numerical variable, and the values are no account, 0, less than 200, greater than equal 200. So it's not the numerical value of those. And similarly, many of these variables are not numerical, but they're categorical. So the first thing you usually do with a new data set is you draw some graphs. So here are some graphs. The red are the actuals who did not default. The blues are the actuals who did default. This is loan duration in months, credit amount in Deutschmarks, age and checking account. And you can see the red versus blue sort of does what you'd expect it to do. The shorter the loan duration, the more likely a person will not default, and conversely, the larger the checking account, the more likely the person will not default, and conversely, and so on. Data analysts use multiple models in their work. Here are 6 common models that can be used. I will only use the first one for this because it's got the best transparency. So I want to use logistic regression. I want to predict the variable that is either 0 or 1. I can't use linear regression for that because linear regression would go on infinitely in both directions. The probability function I'm going to use is 1 over 1 plus e raised to the negative beta 0 plus beta 1x. With some algebra, if you take the odds ratio of that and natural log it, you get a linear expression, beta 0 plus beta 1x. And the parameters beta 0 and beta 1 will be determined for maximum likelihood. This is a typical logistic regression curve, and note that it's sort of S-shaped and ranges from 0 to 1. How should we measure model performance? So every actual value is either 0 or 1, and every predicted value is 0 or 1. So therefore, every value falls in one of these four states: true negative, false positive, false negative, true positive. A humorous example of false positive is the male who's given a pregnancy test that comes out positive. That's a false positive. The main measure we're going to measure performance will be accuracy. True negative plus true positive divided by the sum of all four of those. Another one is area under the ROC curve, which measures how well the model distinguishes between true positives and false positives. So for simplicity, I'm going to start with model 1. I'm going to partition the data into a training set and a testing set. I'm going to build a model with the training data, but evaluate it with the testing data that the model has not seen. And model 1 uses just one independent variable for illustration. I've chosen loan duration. This gives me these two parameters of B0 and B1. Remember Joe? Joe is in the training data. His loan duration was 24. So plugging that in with the equation I developed from the logistic regression gives me a probability of defaulting of 0.337, which is fairly low, which suggests he will not default. Constructing a linear credit score, he gets a score of 665, which is a pretty good credit score. This model was too simple. Joe did default. The score was too high. Model 2 is a more realistic model. I considered combinations of many variables. I chose these 6. And note that because many of these variables are categorical, they need to be transformed into dummy variables. So the checking account is going to be transformed into these 3 dummy variables so they can be input into the regression. The logistic regression with these variables, I was able to compare the variable importance using the absolute value of the z for each variable. A large checking account is most important, followed by loan duration, and so on. Now we'll go to model 3, which is the bank industry model, which is a little different from the model I just created. I'm going to use the same variables as my regression formula, but I'm going to do 2 additional things that the bank industry does. I'm going to put my continuous variables into discrete bins, and I'm going to calculate a new variable called weight of evidence, WOE, which measures the strength of each variable in separating the defaulters from the non-defaulters by bin. This helps smooth the variables to have a monotonic and logical relationship with WOE, and these WOE values become the independent variables in the regression. So for the first variable, loan duration, this is what the WOE calculation looks like, and there's a similar calculation for all the other variables. I've created 5 bins for loan duration. For each bin, I count the non-defaulters versus the defaulters. I calculate the distribution of the non-defaulters and the distribution of the defaulters for each bin. And then I take the ratio of those 2 distributions natural logged. When I graph that, that looks like this. Notice that they are monotonic, and this illustrates the predictive strength of loan duration in separating the non-defaulters from the defaulters. Now, the industry practice on scoring is that we want scores to vary linearly with the natural log of the odds ratio. And further, we pick two arbitrary but sort of baseline assumptions. We want a specified odds ratio at a specified score, and commonly it's at a 600 score. We want a 20-to-1 odds ratio. And we want a specified rate of change of odds. So, for example, we want to double the odds for every 50 points. And remember, the WOEs are weights for each variable. So those two sort of initial conditions will be used in a linear calculation of score. We're going to solve for A and B based on those two initial conditions. And then the score will be A plus B times the natural log of the odds ratio, and solving for A and B. The resulting credit score versus probability is a nice smooth curve. I didn't have enough really large probabilities of default at the large end, so it kind of flattens out. Here's the distribution by credit score. Unfortunately, I had some scores under 300. Nothing in the calculations prohibited that, but I want the lowest score to be 300, so I put those lowest scores in the 300 category. When I recalculate that prior distribution by credit score band, the 5 credit score bands look like this, and other than a few too many in the lowest band, this is sort of what you expect. You want most people to be in the middle, not too many people at either end. The model summary. Model 1 had the lowest accuracy and area under the curve. Model 2 and 3 did better. I would have expected Model 3 to be better than Model 2, but that didn't happen. Getting back to Joe, Joe's probability of default worsened with each model. With Model 3, it was 0.446. With Model 3, Joe's credit score was 400, which I think is much better than his 665. Joe had a large credit amount, 11,560 Deutschmarks, which was a lot for the time, and he actually did default. Before putting this model into practice, we'd consult with the domain experts. We'd like them to do a sample of decisions of a few observations and compare those to the scorecard. We'd like the domain expert to ask if this is the desired distribution of scores. Have we changed the risk profile unacceptably? And perhaps if we had, we would go back and recalibrate our model. A few things we did not consider in this is we sort of arbitrarily picked a probability threshold of 0.5. On probability greater than 0.5 is default, less than 0.5 is not default. We could calibrate that if we wanted to change the distribution. We could have recognized the cost of misclassifying is considerable, and that would change the p-value perhaps to 1/6 instead of 1/2. We ignored a lot of variables, particularly the year and state of the economy, which would make a big difference. We could have used other models, but the logistic regression is the most easiest to explain. Here are my references. One is a book, one is a website. I learned a lot from this. I learned that the banking industry does this a little differently than the rest of the math and data analysis world. But this is a good exercise in both logistic regression and understanding both credit as a data set and credit scoring. And I hope you enjoy this.